Now let's have a look at example 8, Maclaurin series, chapter 2. In part A, you are asked to express, let's call it y is equal to ln of 1 plus x. Actually, let's call it f of x, it would be easier for Maclaurin series. We're infinite series in ascending powers of x. So, copy the expansion from the formula booklet. So f of x can be approximated by the polynomial f of 0 plus f dash of 0 x plus f double dash over 2 factorial x squared, etc., etc. So, what I like to do, the way I set it out normally, let's put the function on the left hand side, and I like to go down the left hand side when I'm differentiating, and on the other side I'm going to evaluate my functions and derivatives at 0. You can do them as you go along, or you can do them later. So I'm going to differentiate this function, so f dash of x, that goes to 1 over 1 plus x, which is 1 plus x to the power of minus 1, so it's similar to the function we evaluated previously. Okay, so minus 1 comes down, so we've got minus 1 plus x, take 1 off, the power multiplied by 1 stays the same, f triple x, I'll do it one more time after that, minus 1 times minus 2 becomes 2, 1 plus x, take 1 off the power, we've got minus 3, f fourth derivative is going to give you 3 times 2 is 6 with a minus 6, 1 plus x to the power of minus 4. Okay, so let's find the values when x is equal to 0. So what do we get? We get f of 0 is going to be ln 1, which is 0, f dash of 0, that gives me 1 to the power of minus 1, that's just 1, f double dash of 0, that just gives me minus 1 to the power of minus 2, that's just minus 1, f triple dash of 0, that's going to go to 2, anything to the 1 to any power, because all those brackets will go to 1, they just are contributing 1 to the answer. So really what we're getting is the whatever is number we've got in front, and these are your values. So let's put down the substitute our values into the formula. So ln of 1 plus x can be approximated by f of 0 is 0, so it's 0, plus 1 times x, so it's x, plus minus 1 over 2 factorial, so it's minus 1 over 2 x squared, plus then you've got 2, it will be third derivative over 3 factorial, so that's going to be x cubed. Since I've got this one, let's write this one, minus 6 over, you need to have 4 factorial if it's x power 4. Notice the pattern, if it's second derivative, it's over 2 factorial and you get the power of 2. If it's third derivative, which I didn't write down, you'll get over 3 factorial and we to the power of 3. Let's just tidy it up. So you get x minus a half of x squared plus 2 over 3 factorial is, you can do it on the calculator, the 2 so will cancel, you've got 1/3 x squared, and this one is 6 over 4 factorial. 4 factorial is 1 times 2 times 3 times 4. Again, you can do it on the calculator. The 6 will cancel, you are left with a quarter, so it's minus a quarter of x to the power 4, and that should be cubed. Write your cubes carefully, and you can actually spot the pattern, so you could see that it goes nicely. So to the power of 4 to the power of r, you would have 1 over r, and that would only, if you want to know how to do the general term, that would be okay for, it's only positive for first, third, so odd numbers, and it's negative for even numbers. So how can I make power of 2, power of 4 negative? You can multiply that, let's just put that like by -1 to a specific power. So if that r happens to be even, I want this to give me the negative answer of -1. So you need to give this an odd power. So you could do to the power of r plus 1 or r minus 1 if you choose. So that would be the general form. Not that you need to know it, but it's just good to have an idea. Okay, so let's have a look at part B. It says using only the first 3 of our approximation. So if I'm going to stop there, I'm not going to put an equal sign. You could say it's approximately equal to x minus a half x squared minus 1/3 x cubed. So using only that many terms in our expansion, so we're only going to draw it as a cubic, we're going to find the value of ln of 1.05. Okay, so what do I need to add here? I need to make my x equal to 0.05. Okay, so not using a calculator, using this expansion. So substituting that 0.05 minus a half times 0.05 squared plus a third times 0.05 cubed. Okay, let's work it out on the calculator. Okay, so this gives me 0.04 7916. 1, 2, 3, 4, 5, 6, 7. Right, let me just grab a calculator because that's what I read off, and we can just check it. Hold on a second. Okay, I'm back. So let's just see what is actually ln of 1.05. There you go. It's actually 0. Let's write it down here. The answer the calculator gives you is 0.048791. Now look at this. We've got 0.04879, and then they differ. So this is correct. This expansion is brilliant. It works for this small value of 0.05, gives you the correct answer of the 5 decimal places. That's pretty strong result. Let's have a look at the second value we want to find. So this time we want to evaluate ln 1.25. So what have we substituted into this? We've got to substitute 0.25. So that's 0.25 minus a half, 0.25 squared, plus a third, 0.25 cubed. If you've got more than one evaluation, even not, like here we've got two, we a third one, so then so rather than typing it this or every single time, obviously you should know that trick. You can write it in terms of ans, so you could do ans minus 0.5 ans squared plus 1/3 ans cubed. Okay, obviously it's put 0 in there, so we're going to just check and put 0.25. Scroll up to find that. That should give me the answer of 0.223958333. So let's check what actually we should have. ln of 1.25. Okay, so the actual answer that the calculator gives us is 0.22314, etc. Now, how accurate are we here? Okay, the same digit up to the third decimal place. However, if I were to round it to the third decimal place, it will be incorrect. So rounding it, it will be correct to 2 decimal places. So this one correct to 5 decimal places, and this one agrees with 2 decimal places. So let's have a look at the last one, which happens to be, let's check, 1.8, so even bigger. So 1.8 means we need to substitute 0.8. I'm not going to write it again, showing I've already shown it twice that I'm substituting. What I'm going to do is put 0.8 equals, and hopefully the calculator still stored my function, which it did. There you go. So the answer I'm going to get is 0.65066. I think it's 6 recurring. Okay, so let's check what should I get if I put 1.8 into my ln. It should have been 0.5877. Right, so this is really different from those two. It's not even correct to 1 decimal place, because this one will round to 0.7, this one to 0.66, so not even correct to 1 decimal place. So you could argue if you want to round it to the whole number, it will be correct then. So why is it? We have to comment on the accuracy of this, of the estimates which we have. So these are our comments, but overall, what you need to learn from this lesson is, as you are evaluating x close to 0, you will get really strong, accurate answers. And if you veer away, diverge away from 0, you are going to get less and less accurate answers, and then completely wrong answers eventually. So it only works for values close to 0. Maclaurin only works for these. Okay, we're going to move on to example 9 next.